you. Okay, so Wade McDonald is a PhD student in computer science, studying with Professor Nathaniel D. Osgood. He is in the Computational Epidemiology and Public Health Informatics Lab, CEPHIL, at the University of Saskatchewan. His PhD research is focused on informing epidemiological simulation models with wastewater surveillance data. Wade originally hails from the town of The Hat, Manitoba. Wade previously studied civil engineering and holds 10 years of teaching experience at the University College of the North in the past. Wade's research interests include simulation modeling and cross-disciplinary application in computer science. Please welcome Wade for his presentation. Wade, over to you.
Thank you very much. I'll just get my slides going here. So I'll begin with a land acknowledgement. At the University of Saskatchewan, we acknowledge that our main campus sits on Treaty 6 territory and the homeland of the Métis, and we pay our respects to the First Nation and Métis ancestors of this place and reaffirm our relationship with one another. I'll give you a brief outline of what I'm going to talk about. We'll do an introduction. I'll discuss the idea of simulation modeling and then agent-based models more specifically. And then I've got some examples from some research I've participated in. One is study of chickenpox and the other is pertussis. And I'll briefly touch on COVID-19 and then look at some tips for running large models using the AnyLogic software. And then finally, I'll introduce some trainings that my supervisor is providing this summer. Oops. So about me, I'll just go through this quickly because Blessing discussed this in his introduction. So there we go. So the Computational Epidemiology and Public Health Informatics Lab at the University of Saskatchewan is led by Dr. Nathaniel D. Osgood. In the Department of Computer Science at the University of Saskatchewan, and it's focused on applying computer-based simulation models, mobile technologies, and big data to understand public health outcomes and policy trade-offs at a population scale. So what is simulation modeling? This is a computer simulation of a complex system. It plays out over accelerated time. It is an approximation, as all models are, but it can provide learning. Compared with statistical models, simulation models have more detail, but pose a greater computational burden. Why build a simulation model? Mainly as a learning tool. A lot of people focus on the ends of a model, like making projections, but a lot of learning with modeling happens in the process of building the model. We can use a simulation model to encode a complex hypothesis so that it may be shared with others, subject to scrutiny, and tested. We may run what-if scenarios. Oops, going a bit too fast there. So we may use a model to run what-if scenarios. Benefits of model studies include that they're less expensive than real-world experiments. There's no risk to health or life because we're dealing with simulated people, not real people. And again, because the people in the model aren't real, there are fewer ethical issues because we're not doing work with real human beings. It's faster. We can test ideas in a simulation model in a matter of minutes or hours that would play out over years or decades in real life. so I'll say something about agent-based modeling specifically. So this is one type of simulation modeling where agents are placed in an environment. The agents are autonomous, so they act independently of one another. They're unique. They have properties which are specific to each agent and may vary across the population. And they locally interact with their environment and other nearby agents. Agents can retain a state that can include their history, and our interest in constructing an agent-based model is observing emergent behavior. So we construct the model with some relatively simple rules, and we want to observe behavior at the aggregate level that may be unexpected based on these rules. Some advantages of agent-based modeling is it allows a simple representation of heterogeneity. The individuality of agents allows us to consider specific subpopulations or individual trajectories. And the local interaction allows us to examine things like network effects and other specific to the individual behaviors. Disadvantages of agent-based modeling is it's very compute intensive, and this scales often superlinearly with population of agents. And it's also less explainable to non-modelers. Current simulation modeling packages require a lot of programming understanding, and while they do use some diagramming languages, they're still more difficult to explain to non-modelers than, for example, ODE models using the system dynamics abstraction. So here's an example of an agent-based model we constructed in CEPHIL for the study of COVID. So this is imagining a New Year's Eve venue, and people are mingling. The big red circles are around infectious individuals. These people move around in this space and interact with each other, and we can observe how many transmissions occur based on the model assumptions. So there are a number of different tools to construct agent-based models. The one we use most in CEPHIL is AnyLogic. Advantages of AnyLogic are that it allows hybridization of agent-based discrete event simulation as well as system dynamics modeling methods. Repast is another popular one, as well as NetLogo, which is free, so that lowers the barrier to entry. AnyLogic is quite expensive. There are many others, and this Wikipedia article is a good summary of those with links to the developer websites. So I said I was going to discuss examples from two studies. So the first we'll look at is a chickenpox model. So this was constructed with principal investigators Dr. Alexander Doroshenko, Dr. Marwa Farag, and Dr. Nathaniel Osgood, who is my supervisor. And the students were Dr. Ellen Rafferty, who spoke at this venue a few weeks ago, myself, and Winchell Chen, who is about to complete his Ph.D. at the University of Saskatchewan. Chickenpox and shingles diseases are both caused by the varicella zoster virus. Chickenpox is a childhood disease. Typically, the virus remains dormant in the body after you've had the disease, and it can reactivate later in life as shingles, which can be very painful. So our first research question with this model was, does vaccination for chickenpox cause increased shingles incidence? So our model key features included a user-defined network of 500,000 agents, an open population, meaning people are born, age, and die within the model, preferential contact age for children, as this is primarily a childhood disease, different connection ranges for each disease, and a bimodal population density that approximates a urban area surrounded by a rural space. So this is the natural history of disease as represented by what is called a state chart in the chickenpox model. So I won't go into great detail here, but we have a maternal antibody state. We have some susceptible states, vaccinated, and then these represent chickenpox disease. There's a recovered from chickenpox, and then shingles down here. There's also a state chart for aging and life and death as we have an open population. So fitting this model, we wanted to ensure that the age distributions of incidence for each disease matched what has been observed in the pre-vaccination era for chickenpox and shingles. So this was for chickenpox, and then this fit was for shingles. You see this flaring at the end of the age range is due to small population effects. So this slide summarizes sort of the key. This represents a paired run of the simulation model with the same random seed. So you can see the two members of the pair follow each other exactly until what we've called time zero, which is the time where the chickenpox vaccination is introduced. And the y-axis is total shingles cases. So we can see once vaccination is introduced, we see an increase in shingles cases and then a sharp decrease. This shows some different assumptions about what is called immunity boosting. So it's posited, and clinical studies are still working on this, that being exposed to other chickenpox or shingles cases after you've had the natural disease can boost your immunity without actually making you sick. But the strength of this effect is not well known clinically. So with our model, we tested various assumptions about the strength of that boosting effect. From the upper left here is assuming a small influence of boosting and then increasing to the bottom right where we assume it to be a very large effect. So we can see in all cases, there was a red is shingles, all of this is shingles incidence, but red is with vaccination. In all cases, we see a certain amount of increase in shingles, but whether it is large or small depends on what we assume about that boosting effect. So this model has been used to test questions on this primary research question of effects of chickenpox vaccination on shingles, also optimum vaccination schedules for chickenpox and cost effectiveness of chickenpox vaccination in Canada. I'll move on now to a pertussis model. So this was done in a group model building process. So the team members were, again, Drs. Doroshenko and Osgood, Dr. Karsten Hempel, who's a postdoctoral fellow working with Dr. Doroshenko, and myself. This formed part of my master's degree thesis. We were further advised by an advisory panel consisting of these doctors. This model was envisioned as an extension of a study co-authored by Dr. Doroshenko in 2016. The primary model builders in this worked independently and then coordinated weekly with video meetings. And then we met with our local co-PIs occasionally to discuss progress, and then had 3 to 4 day intensive work sessions where one of us would travel to the other's location and work intensively on the model, and approximately quarterly meetings with the advisory panel to discuss progress and retain their advice on how we should proceed for the next stage. Some key model features in this model was a tile-based space allowing for varying population density patterns, a distance-based network. Schools and households were created as contact venues within which people could expose others at the same venue. We implemented a data structure to optimize range searching, and I'll say a bit more about that later. And it had a continuous representation of immunity state, where a person's immunity would wane over time and the severity of their infection would depend on the infection level of the exposure as well as their own immunity level. This figure sort of represents how the population was networked. So if yellow is a person of interest within the model, each person has a household, which are the white squares. They're connected to other people within a certain radius of themselves, which are the black dots. And they're also associated, if they're of school age, with a school and connected with all the other students in the school. This shows the contact pattern emergent from the model. So most people primarily contact people of their own age, which is represented by the strong diagonal. And then we have off-diagonal features. So this represents children exposing their parents, and this represents parents exposing their children. And then there's some fainter signals of grandchild-grandparent interactions. So our health research question in building this model was, can immunization of expectant mothers in the third trimester of pregnancy reduce incidence of pertussis in infants? So given our model assumptions, immunization during pregnancy can reduce pertussis incidence significantly in the 0 to 2 month age group, which is the primary risk group for severe pertussis. Now, it's worth mentioning that this is looking only at the epidemiology of the situation. There's certainly much going on within the body, and our model doesn't simulate that. So it's certainly not exhaustive, but it suggests that this may be a viable focusing on this group may be a viable intervention. So should we do it? Maybe. Clinical trials will be necessary to prove safety. Vaccination during pregnancy may be a tough sell to expectant mothers. And in Canada, especially where we have government paid healthcare, a big question is, will the government cover the cost of the vaccines? This kind of intervention is actually now being implemented in several jurisdictions. So it appears to be a viable strategy, but is it the best? So that is another question that remains open after this study. And now I'll say a little bit about COVID-19. The Computational Epidemiology and Public Health Informatics Lab worked closely with the Saskatchewan Health Authority during the pandemic to develop Saskatchewan's modeling infrastructure to help mitigate the pandemic. Multiple simulation models were constructed of different types. We attempted to anticipate the spread and the healthcare needs and the needs of the healthcare system throughout the pandemic. We examined what-if scenarios for mitigation. Oops, I'm going a little bit fast again. My personal takeaway from this is that science communication is very important, and it's not something that I have studied academically or that I would consider myself to be strong in. But I think we had a problem communicating the results of the models to people in terms that those people, be they government or members of the public, could easily understand. So I think that's a big takeaway. Some of us modelers might be technical and like to focus on the computer side of things, but there's certainly an interface with human beings that is a very important part of it. And the next section, I'll briefly discuss some tips for large any-logic models. So things that are expensive computationally include random number generation, range searching, which means determining how many agents are within a certain distance of a given agent, setting up the network of the agents, message passing, where agents send messages to each other, such as indicating an exposure to a pathogen, and events scheduling, as well as graphics rendering. So some suggestions that I have if you're using the AnyLogic tool, and these can possibly be applied to other tools as well. Use special data structures. In the chickenpox model, we constructed a grid data structure to speed range search, and with the pertussis model, we implemented one called a KD tree. But since those projects, I've learned that it's actually much better to pre-compute your population and its network and load it from a file or database, rather than randomizing it every time the model runs. And if you want to work with several different populations, you can make several pre-computed populations to use with the model. Minimize message passing. This is an important part of the modeling system, to be able to pass messages from agent to agent, but doing it excessively will slow down your model. Reduce events. So don't trigger an event that infrequently actually does any work, because it takes up time in the scheduler and slows down the model. Put graphics in a separate so-called agent, so that you only need to bring them into the model when you're running it to show to stakeholders or for feedback in real time. And then that will save a lot of computation and memory. So I want to show some diagrams here. These are two state charts of two different ways we may implement an SIR mechanism within AnyLogic. So in the one on the left, agents begin as susceptible. They receive a message of exposure at a certain rate, and then there's a certain probability of infection on contact. This decision point determines whether they're actually infected by that exposure. If not, they return to susceptible. If it infects them, then they move to infective. This transition represents exposing other agents while they're infective, and then eventually they become recovered. On the right is a similar mechanism implemented in a different way. So people begin as susceptible here. On the messages now instead represent infection and not exposure. So a person, when infected, will move to infective 2. This represents infection of other agents. So what it does is it determines an agent to contact. It rolls the probability of infection on contact first and only sends a message if the second person is infected. So what this does, on the left, we have many, many exposure messages that do not result in infection. And on the right, we only send messages when there's an actual infection happening. So this reduces the number of messages in the system and therefore speeds up the model. So would you like to learn more about this? My supervisor, Dr. Osgood, is running 2 training sessions this summer. One is the Bootcamp on Systems Data Science. And this is practical combining of data science and system science for health. This runs June 27 to 30 of this year, and it can be attended in person in Saskatoon or remotely. And then a second training session is on agent-based and hybrid modeling. It's called a Bootcamp and Incubator. And this will involve conceptualization, formalization, and implementation of simulation models for insight into health problems with the AnyLogic tool. This runs August 22 to 27 of this year, again, in person in Saskatoon or remotely online. So contact Dr. Osgood at this email if you're interested. So I'd like to thank you for your attention. I'll just put on the screen some of the publications that I've co-authored that are relevant to these models that I've discussed, and I'll turn it back to Blessing for question and answer period. Thank you.
All right, thank you very much, Wade. And I'd like to know if there is any question for Wade. Before I start, I would like to read some of the Q&A that came in. Wade, this is coming from Christine Lewis, and it says, I'm curious on the choice of using a continuous parameter for immunity. What pros / cons does this have to from this discretized alternative? Okay, so I don't know if are you seeing the question or should I take it again for you?
Yeah, no, I can see the question, so thanks for that.
Okay.
I'm going to go back if I can here.
Yes, you can.
To the previous slide. So this this example represents a discrete representation of infection. So while you're infective, the degree of infectiousness does not change. So from the time you enter this state, you're infecting people with equal strength to just before you leave it to recover. This, in an agent-based model, this is a simple implementation and would therefore be computationally efficient, but it loses some aspect of the actual infection system that we might consider. So when a person is infected with a pathogen, they're like, assuming it's a virus, their viral load varies over the course of the infection, and the amount of virus that they're shedding into the environment also varies with that viral load. So a person who is newly infected may not be as infectious as someone who's had the sickness for a number of days, and they may be more infectious than someone who's had it for a week or two. We see this as a key feature in COVID-19, where people are actually quite infectious before they start to show symptoms. So it's an additional level of detail that can potentially inform the model to make it more realistic, but it also requires additional data. So we need to look at research about virus shedding over the course of the disease. But the thing I should point out is both of these can be considered fairly strong assumptions. So this is kind of a typical design pattern in an epidemiological agent-based model, and people may not bat an eye at it as compared to a continuous representation, but they represent different assumptions about the way that the disease spreads that may impact emergent behavior that we're observing in the model. So I guess another downside of the continuous representation is more computation. So I hope that answers your question.
Okay, thank you very much, Wade. I don't know, Christian, I hope that answers your question. Christian, all right. Okay, so we have some other persons here. Zoe would like to ask a question. Zoe, over to you.
Christina is asking questions.
I believe we have to allow an attendee to talk.
Let me see. Yeah, he's there already. I told him.
Okay, I think I got it. Is that working now?
Yes.
Yeah.
Yes. Okay. Hi, Wade. Thank you so much for this talk. You made it really easy to follow despite it being a difficult subject. And I wanted to ask, in your experience, what do you think makes science communication effective? Or another way of saying that, what really doesn't work when it comes to science communication, and what should we do instead?
Well, I guess the reason I got that takeaway is not because I've been an effective science communicator or part of a team that effectively communicated. I feel like myself and our group kind of dropped the ball in the pandemic in terms of spreading the message of the outcome of the models. So I think you need to know your audience. You need to understand that they may be skeptical and address the issues on which they may be skeptical of these methods. And if you have the opportunity to work with someone whose profession and field is communication, especially science communication, I would certainly recommend that. Does that address your concerns?
Yes, thank you.
Thanks.
All right. Thank you very much, Zoe. Professor Wu, I think you wanted to say something?
No, I think Zoe, Zoe, you still raising hand?
Sorry, let me lower that.
Okay, good, thank you, Zoe. So, Wade, so, I mean, it's the agent-based simulation group in Saskatchewan led by Professor Oscar. It's absolutely the first rate. I understand you're also going to have a summer training program. I assume you're going to talk about in a moment again. But how much computing power is required if a student postdoc want to do a project? Would they have the computing power to do all the agent-based simulations?
Well, if we look at the examples I showed in my talk, the chickenpox model would run on a fairly modest computer, but it would with about 16 gigabytes of RAM and a fairly old processor, I think. Because this study took place several years ago, and we were using the computer lab, the student computer lab at the U of S, which had some fairly old machines in it. It would take about 6 hours to run the model in earnest, but for testing purposes, we would run with a smaller population that would allow us to get a faster turnaround. So it required quite a bit of computation time, but a modest hardware requirement for doing those computations. The pertussis model required a lot more memory, and we had to run it on servers that were high performance computing facilities at the University of Saskatchewan. So and it would take probably a couple days to run one realization at the full 500,000 population. So that is a bit more demanding, and it would depend on what resources you have available, whether you could run a model of that complexity. So I think it depends on how much detail you want to throw in your model, but it can range from being able to run on a dated laptop to requiring high performance computing resources.
Good, thank you. Would be any issues running this through cloud computing and with public health data, which will require certain security?
Well, the computers that we used at the U of S for the COVID model were vetted by the Saskatchewan Health Authority for security, and they were used only for that purpose during the pandemic. So it wasn't a public cloud provider. It was a university system that was vetted by the stakeholder for adequate security. And if you're dealing with actual personal health information that's subject to ethics considerations, that is very important. The chickenpox and the pertussis models were based on publicly available aggregate data, so we didn't have those kinds of concerns running those. So for some of the chickenpox model runs, we used Amazon cloud service to run them. And that wasn't a concern because there were no individual personal health information involved in the model. It was all publicly available aggregate data.
Great, thank you.
Okay, thank you very much, Professor Wu, for the question, and thank you, Wade, for the answer you provided. So there are some couple of questions that are here. Chingju is asking, did I mix the part about training opportunity? Wade, did you hear me?
Sorry, could you say that again, please?
Yes, I'm saying that Shongu sent a question on the Q&A.
Okay.
So did I mix the part about a training opportunity?
Okay, I'll put that back on the screen. So the first training opportunity is here, so feel free to screenshot this. It's June 27 to 30 of this year. And the second one is on August 22nd to 27th of this year. And again, feel free to take a screenshot. Contact Dr. Osgood at this email if you're interested in participating.
All right. Thank you very much for the answer. There's another question for you. Martin wants to ask you a question. Martin, please, over to you.
I think I'm going to click allow to talk for Martin, and hopefully he can.
Hello, can you hear me now?
Yes, we can hear you. Go ahead.
Sorry about that. I attended a course a long time ago when I was working for the USGS National Wildlife Health Center. It was on using their high performance cluster Yeti. And I remember the person who was giving the instructor said he'd had an issue with someone developing code for a model in MATLAB, and then the license basically being prohibitive from running it on a HPC due to the cost of them becoming per node or per CPU. I can't remember which, but you can imagine it soon stacks up. I was wondering with any logic, is there any similar issues when you say develop a code to say just do the debugging and testing on a laptop, and then to do the many iterations you need to do to get decent level of sort of confidence intervals for forecasting and so on, when you then come to run it on a HPC? Because if they start charging you per node or per CPU, that could become quite exhaustively expensive.
I agree. The AnyLogic licensing terms, like it is fairly expensive software, but one of the licensing options, which is an additional amount of money, but over the base version, allows you to export the model as a standalone Java app that you can then run on any machine that has a Java virtual machine, including high performance computing systems. So there's no, to my knowledge, per CPU or per node licensing fee. I believe it's a per user licensing fee.
Right.
AnyLogic also offers their own cloud service, both as a publicly facing service provided by the company and as a private cloud that users may install on their own hardware. And I don't know what the costs are associated with that. It's probably substantial, but I suspect it's a per installation fee, not a per CPU or per, so it's a different licensing scheme than MATLAB, so possibly more friendly to that, I think. Like, we didn't encounter any licensing issues running the models we built on HPC. Does that answer your question?
Yeah, I was just curious because I was aware that could be an issue. With MATLAB, at least, that's why I moved to Python.
Thanks.
All right. Thank you very much, Martin, for your question, and thank you, Wade, for the answer you provided. Do we still have any other question? Okay, Martin, could you please lower the hand on the section? All right, thank you very much. So if we do not have any other question, we would like to come to the close of this meeting today. And on behalf of Professor Ali, I'd like to thank all the speakers, especially Wade McDonald for his wonderful presentation today, and the panelists, Professor Wu, Magdi, Nedamati. I'd like to thank all the participants. Thank you very much for attending. And for the record, this is the last presentation or the last meeting for this series. So further meetings will definitely be communicated to everyone. And Professor Ali would like to say thank you for participating. Thank you for all the good work. And see you when we meet again. And from me, I will also say thank you very much for your time, and thank you for having me as well. Thank you.
Thank you for this opportunity to speak. Have a good day, everyone.
Thank you.